Hello everyone, today we will be concluding our discussion of scheduling problems with what is known as the critical path algorithm. Now, the critical path algorithm is a pretty reliable method for solving scheduling problems that generates a priority list based on the concept of a critical path, as the name implies. Now, a critical path basically is whatever path from the start of a project to the end is going to have the highest overall processing time. And when we are using the critical path algorithm, the first step is to figure out the critical path for the project using what is known as the backflow algorithm. This allows us to calculate the critical path and the critical time for the project. And then we use the information that we get from the backflow algorithm to create a priority list. The critical path algorithm is a pretty effective way, usually gives us, it's really one of the best algorithms for solving scheduling problems because it relies on this concept of the critical path. So the backflow algorithm, the way that this basically works is we are going to take every single vertex on our project diagram and we are going to figure out what we call the critical time from that vertex to the end. The critical time is basically the longest possible processing time for any path from that vertex to the end. So we're going to use square brackets to indicate critical times. The end is going to have a critical time of 0, and then we're going to work backwards from there. So for any given vertex, the critical time is the processing time for that vertex plus the highest critical time of anything that that vertex points to. So in this case, F and G both point just to the end. So the critical time is just going to be the processing time for those vertices. So that's 5 for F and 2 for G. If we work backwards from those, the next things that we see are D and E. So for D, D points to F and G, of which F has the higher critical time. So our critical time for D is going to be its processing time 4 plus the critical time of F, 5. So this would put us at a critical time of 9 for D. We're going to do the same thing with E. E only points to F, which has a critical time of 5. So processing time of 4 plus critical time for F of 5, that's going to give us 9. This is our critical time for E. Now, if we work backwards again, we have vertices A, B, and C. So let's start with A. A has a processing time of 2, and it only points to E with a critical time of 9. So 2 plus 9, that's going to give us 11. And then for B, B only points to D. So 5 plus 9 is going to give us 14. And then finally, C also only points to D. So 3 is our time for C, plus 9, the critical time for D, that's going to give us 12. And then finally, we can go back to the start. The start has a processing time of 0, so the critical time for the start is going to be just whatever is the highest critical time that it points to. In this case, that's B with a critical time of 14. So our critical time for the start is 14. And we would say that this is the critical time for the entire project. This is basically the longest time for any path from the start to the end. Now, one thing about the critical time is that it is impossible to finish a project in less than the critical time. So, this brings us to the concept of the critical path. Now, the critical path basically is just the path of highest critical times from the start to the end. So in this case, from the start, the highest critical time that we see is B, and then D, and then F, and then to the end. So from start, B, D, F, end is going to be our critical path for this project. All right? Now, the next step is to create our priority list. So when we are using the critical path algorithm, we are going to create the priority list starting with whichever task has the highest critical time rather than processing time, and then go from there down. So the highest critical time that we see on here is B at 14. So B5 is going to be first on our priority list. Next, at 12, we have C3. Then A2 at 11. And then we have a tie between D4 and E4, both at 9. And then next we have F5 and then G2. So we would call this our critical path priority list. So now we're going to make the schedule in basically the same way that we have in the last couple videos. So from the beginning, B, C, and A are ready from the get-go. So our priority list says that B and C should be first. So we're going to give B to P1. And then C to P2. Next thing that happens is we finish C. So once we finish C, note that D is still not available yet because we haven't finished B yet. So the next thing that we're going to start on is going to be A, our next available task, with a processing time of 2. Next thing that happens, A and B finish at the same time. So this is going to open up D and E. So we have 2 processors available, so we can start on these at the same time. Next thing that happens, D and E finish at the same time. That opens up F and G. So we're going to give F to P1 and G to P2. Now you'll notice that in this case, after G finishes, we have some idle time for P2, 3 hours, while P1 is finishing up with F. Now, one thing that you'll notice about this is that our finishing time for this is 14, which is the same as our critical time. Now, we said earlier that it is impossible to finish a project in less than its critical time. So what this tells us is that this is actually an optimal schedule. So we would say that this is our optimal finish time, and that would be 14. Notice also, if you watched the last couple videos, that all 3 of these algorithms, simple alphabetical priority list, decreasing time, and critical path, all gave us the same finishing time for our schedule. That is not always going to be the case. In fact, most of the time, of the algorithms that we've talked about, this critical path algorithm is usually going to be the best one compared to doing a simple alphabetical priority list or the decreasing time algorithm. It just so happens that in this case they all worked out to give the same finishing time. Thank you for watching, and I'm happy to help with questions as always.